Okay, so today I'm going to go over the last section in chapter 8, 8.4. We're going to look at, well, chapter 8 is all about um, hypothesis testing, and we've looked at already two cases. 8.2, we looked at the case when someone makes a claim about a population proportion, and then 8.3, we looked at cases where people make claims about population means. And so today, the last case, we're going to look at claims about population standard deviations or population variances. They're both very similar. So I'm just going to look at this problem from the homework. This is number 2 from 8.4. And says a simple random sample of pulse rates of 50 women are drawn from a normally distributed population, and it results in a standard deviation of 10.6 beats per minute. So they, randomly pick 50 women and measure their pulse rates. But so you have 50 different pulse rates for these women, and I guess they put them in a spreadsheet or whatever. But what they give us is not the average pulse rate. They don't give us a sample mean. They simply give us the standard deviation and the pulse rates. Okay, so the 10.6 beats per minute is the standard deviation from the sample of the 50 women that they sampled. Okay, and then it says, the normal range of pulse rates of adults is typically between 60 to 100 beats per minute. And it says if the range rule of thumb is applied to that normal range, the result is a standard deviation of 10 beats per minute. And so basically what they're saying there is from that information that they just gave us there, that they believe that the standard deviation should be about 10 beats per minute, the population standard deviation. And so they say use the results with a 0.05 significance level to test the claim that the pulse rates of women have a standard deviation equal to 10 beats per minute. Okay, and then we're just supposed to go through and sort of work out the problem. All right, so what's going on here? So the population here consists of the pulse rates for all women. And the claim that's being made is about the standard deviation in those pulse rates. So again, if you were to go to every woman and measure their pulse rate and put it into a spreadsheet, what we want to know about the population is the standard deviation in those pulse rates, not the mean of the pulse rates or anything like that. We're looking for the standard deviation in the pulse rates. So the claim that's being made in this case is a claim about the population standard deviation, which is sigma. Now, if it were a claim about a mean, like the mean pulse rate for all women, and that would be something that we talked about in the previous section, right? This one's about making claims about standard deviations or variances from the population. And so to test this claim, they sample 50 women and measure the pulse rate, the standard deviation and the pulse rates for those 50 women. And this is the sample standard deviation S. Okay, so anyway, let's work through this. I'm going to go through and, we're going to test this claim. I'm going to go through the traditional method first, and then we'll do the p-value method. Remember, there's two ways of doing this. You can do the traditional method for hypothesis testing, or you could do the p-value method. And I'm going to do the traditional one first, and then we'll do the p-value one. Okay, so remember, the first thing you want to do when you work out these hypothesis testing problems is identify the claim and write it down mathematically. So let's start there. If you read through this problem, at the very end it says use a 0.05 significance level to test the claim that the pulse rates of women have a standard deviation equal to 10 beats per minute. So what they're claiming is that this sigma here from the population is actually equal to 10. So that's the claim. Okay, and then so that's where you start, right? Start with the claim. And then once you decide what the claim is, you have to decide whether this is the null hypothesis or the alternative hypothesis. And this one happens to be the null hypothesis, because remember, the null hypothesis always has an equal sign in it. So this one must be the null hypothesis, H sub 0. So in this case, the claim is actually the null hypothesis. In the past, I've done the problems I've done in the past, they always were the alternative. This is the first time we've had a situation where claim is actually the null hypothesis. And there's some things that happen differently because of that when we make our conclusion, and I'll talk about that when we get to the end. So then what would the alternative be, right? The alternative hypothesis. Well, it's the other hypothesis, and it's either equal to 10 or not equal to 10. So that's the alternative hypothesis. And this is the first time we've ever had an alternative hypothesis with a not equal sign in it. We've done less than and we've done greater than. This is the first time we've had not equal to for our alternative hypothesis. And what happens in this case is, when this was alternative was greater than, then you'd have a right tail, right? This would be called a right-tailed test. If it was less than 10, the alternative hypothesis, then you'd have a left-tailed test. Arrow points towards the tail. When it's not equal to, you have a two-tailed test. So this is a two-tailed test because it's the alternative is not equal to. And on top of that, the distribution that we're going to be working with in this case is a chi-square distribution. If you remember, standard deviations and variances have chi-square distributions. So there's kind of three different distributions that we're working with in this section. The proportion, claims about proportions were z-scores or normal distributions. Claims about means, when sigma is not known, turned out to be t distributions. And then claims about standard deviations or variances, which is this section, have a chi-square distribution. And if you remember, a chi-square distribution starts off at 0 and it goes to infinity. So you can't have a negative chi-square number. And when you look at the distribution, it's not symmetric. And so this is why this, has no symmetry to it. Okay, so just keep that in mind. The distribution is not symmetric. Looks like this. So anyway, let's go through the traditional method now. This is how this is your hypothesis. You write those down first, and the claim is attached to the null. And after you do that, with the traditional method, the next thing you're going to do is find the critical values, which are the boundaries will help you decide whether you're going to reject the null or fail to reject the null. Okay, and if you look at the problem, remember that they want us to use a 0.05 significance level to test this claim. So that's our alpha. Remember, that's the total area in the tails, and we call that alpha. Okay, but this time we have a two-tailed test, right? Because the alternative is not equal to. So we're going to have to take this and divide it equally among the two tails. We have a left tail and a right tail. So just make sure that, you take this 0.05 and you divide it by 2, because the alpha is the total area in the tails. So we want the same amount in each tail, so we have to divide that by 2 to get the same amount. So it's going to be 0.025 in each tail. And then we're going to find the chi-square values where this occurs, right? We want to find the chi-square value here, which has an area of 0.025 to the right of it. And also we're going to find the chi-square value here, which has an area of 0.025 to the left of it. So this is called chi-squared left. This one's called chi-squared right. Okay, so let's find those critical values. And of course, you can't do this on the calculator. Unfortunately, they don't have a calculator function that does this. So you're just going to have to use a chi-square table. And I pulled up a chi-square table from, you can just search on the internet, like Google it and you can pull up a chi-square table. So notice again at the top, it says the areas at the top are areas to the right of the critical value. So let's start with the one on the right. Let's find this one. So if you want to find this chi-square value, table is asking for the area to the right of it. So the area to the right of this would be 0.025. And also remember, the degree of freedom is one less than the sample size. So degree of freedom here would be, our sample size was 50, so it's 50 minus 1, so it's 49 degrees of freedom. Okay, so I want the area to the right to be 0.025, which would be this column here, the third one from the last. And we're going to scroll down till we get to 49 degrees of freedom. And it looks like the closest thing we have is 50. So that's going to be close enough. Doesn't have 49. So when it doesn't have the exact number, just take the closest one. And third column from the right is 71.42. So that's chi-squared right. Okay, and then chi-squared left. The thing we know about chi-squared left is it has an area of 0.025 to the left of it. But the table wants the area to the right of that. So you just have to say 1 minus 0.025 to get the area to the right of it, and you're going to get 0.975. There's 0.95 in the middle here because 1 minus 0.05 is 0.95. So you could also say 0.95 plus 0.025, and you'll get 0.975. But either way you do it, the area to the right is 0.975. All right, so then go to the table, look up 0.975. Let me just see which column that is. That would be third column from the left. And remember, the areas up here up to 1. So the first column and the last column, the area adds up to 1. So those go together. Second column and then second to last column adds up to 1. So these go together. And then third one, 0.975 and 0.025 add up to 1. And that's the columns that we're using. So if you're using the third column from the end over here on the right, you should be using the third column over here from the left. So this makes sense, right? 0.975 and 0.025 are the two columns that we're using. So anyway, scroll down to 49 or 50, and you get 32.357. Okay, so those are our critical values. In other words, the boundaries that will help us determine whether we're going to reject the null hypothesis or fail to reject. Okay, so that's the first thing to do in the traditional method. Okay, and now let's run the test. Run the hypothesis test. Okay, now when you run the hypothesis test, remember, the first thing you do is you make an assumption about the population. And in this case, we're going to assume the null hypothesis is true. And the null hypothesis says that sigma is 10. So for just a moment, when we run the test, we're going to assume that this population has a standard deviation of 10. Okay, so assuming the standard deviation is 10 from the population, we're going to find our test statistic, which in this case is a chi-square value. And you calculate that chi-square value by taking the sample size minus 1 in other words, the degree of freedom, and you multiply it by the sample standard deviation squared, which we call the sample variance, and you divide it by the population variance, sigma squared. That's how we calculate the test statistic. Okay, so let's see what we get. So, the sample size is 50, so you just say 50 minus 1, which is 49, 49 degrees of freedom, times S squared. So here's our S, 10.6 squared. Divided by sigma squared, and we're assuming sigma is 10 when we run the hypothesis test. Now, one thing I want you to notice here is that if you're drawing samples from this population where sigma is equal to 10, then you would expect the sample standard deviation to be somewhere close to 10. So if S were 10, 10, it's close to 10, but what if it was exactly 10? If this was exactly 10 top, you would have 10 squared for S squared, but you'd also have 10 squared for sigma squared, and those would cancel out, right? That'd be 100 over 100. Those would cancel out, and you'd be left with 49. And 49 is right in the middle of these two square values. That's what we would expect to happen if sigma really is 10. Now, we didn't quite get 10 for S. We got 10.6. So it's not going to be exactly, these aren't going to cancel out exactly. We're going to get, not exactly 49 because these aren't going to cancel out perfectly. So the question is, how far is it going to push it from 49? Okay, 49 is kind of the middle, I would say, right? Middle occurs when this is 10, which is the same as what sigma is. We're a little bit above 10, we're at 10.6. So let's see what we get. All right, so it's 49 times 10.6 squared divided by 10 squared. So our test statistic is 55.0564. Now remember, if this was 10, as we would expect if you're drawing from a population where sigma is 10, then this would have been 49. So the fact that this is 10.6 instead of 10 pushes it up a little bit from 49 to about 55. So our test statistic lands right in here, 55. And now notice that that does not land in the critical region, right? Remember, these are called critical regions. This is a critical region on the left, and there's a critical region on the right. This test statistic did not land in either one of those critical regions. And if it doesn't land in the critical region, so if the test statistic does not land in the critical region, if you remember, we talked about this before, and you fail to reject null hypothesis. Now, why am I failing to reject the null hypothesis? Because what this is indicating is that 10.6, my sample standard deviation, is not that far from my assumption about the population standard deviation being 10. If it had gone past 71.42, my statistic, then that's when I would say that the sample standard deviation is too far away from 10, and then I would actually reject this null hypothesis, which says that sigma is equal to 10, which is my assumption. So I failed to do that, okay? And so a failure to reject the null in this case, now I want you to be careful about how you write this conclusion because it's a little different than what we had before. I want you to think of it this way. We're failing to reject the null hypothesis here, and the null hypothesis is the claim. They're the same thing. So if someone says, I'm failing to reject the null hypothesis, you're, in this case, also saying that you're failing to reject the claim. So in non-sophisticated words, you could just say, if you wanted to, fail to reject claim as a conclusion, right? Failure to reject null is the same as saying failure to reject the claim if the claim and the null are the same thing. But my math lab doesn't use, my math lab uses more sophisticated words to get across this same idea. I'm perfectly fine with you thinking of it this way if it's easier for you to think of it this way. Failure to reject the null is a failure to reject the claim. But in more sophisticated words, you could also say there's not enough evidence to warrant a rejection of the claim. That's the way my math lab is going to word it. Quite honestly, that last statement, there's not enough evidence to warrant a rejection of the claim, is just a fancy way of saying that you have failed to reject the claim. There's not enough evidence to warrant a rejection of the claim. You have failed to reject the claim. That's all that says. So my math lab is going to state it in those fancy terms, but just means you're failing to reject the claim, which you can get directly from here, right? If you fail to reject the null, then that means you're failing to reject the claim. So notice what's happening here. This is an unusual situation. When the claim is attached to the null hypothesis like it is here, there's no way to support the claim. Because the claim is that sigma is actually 10. And when someone claims a population parameter is exactly equal to something, that is really difficult to prove because this is 9.9 and that's not 10. If it's 9.99, that's still not 10. So if someone says, I'm claiming sigma is 10, it's very difficult to prove that it's exactly 10. I mean, I guess the only way we'd actually be able to prove it's exactly 10 is if you measured the pulse rates for all women, calculated this population standard deviation, and found it to be exactly 10. So when someone claims a population parameter is equal to something, it's in terms of hypothesis testing, there's no conclusion that would ever say there's evidence to support the claim. The best outcome that you can have is that there's not enough evidence to reject the claim, to warrant a rejection of the claim. That's what happened here. So this is the best case scenario for someone that's claiming sigma is equal to 10. We can't reject your claim. And the reason we can't reject it because 10.6 is not that far away from 10. In terms of a chi-square value, it's at 55, and 55 does not land past 71, nor does it land past, it does not go above 71, and it doesn't go below 32. So let's play with this a little bit, and I'll do the p-value method in a second. Well, maybe I should do the p-value. Let's do the p-value method first, and then I'll go back and play with this. What I want to do is let's change this eventually I'll change this to a different number and we'll make it like really big, like 20. And we'll see what kind of chi-square value we get. And then we'll make it really small, like 2 or 3 or something, and see what chi-square value we'll get. And I'll show you that in those cases, they'll land in the critical region. Um, yeah, I guess I'll do it now, but I just want to remember, let's keep this in mind. So let me just do this as, I guess I'll just do it up here. So let's go ahead and do it now. So suppose S was 20 instead of 10.6, okay? Then what would your test statistic have, what would it have been? Playing around with this a little bit so you can see how this works. So then the only difference would be this would, instead of 10.6, you put a 20 in right here, right? So then let's just see what this is, okay? So 49 times 20 squared divided by 10 squared would have been 196 for chi-square value. I probably picked a number way too big, but it gets the point across. So this turns out to be 196. Then test statistic, it's above 71, right? So then that would land in this critical region at the top up here. And so then you would reject the null hypothesis. Because if the test statistic lands in the critical region, then you reject the null hypothesis. And so then rejecting the null hypothesis is rejecting the claim. Those are the same thing. And in fancy words, you would say there's sufficient evidence to warrant a rejection of a claim. Instead of saying there's not enough evidence, you would say there is enough evidence to warrant a rejection of the claim. Okay, so why is that happening? Why am I rejecting this claim that sigma is 10? Or the null, let's go with null. It's the same as a claim, but why am I rejecting the null hypothesis that sigma is 10? Remember, that's the assumption that we made when we ran the test. The reason we're rejecting it is because 20 is the sample standard deviation that I got. When I sampled 50 people, my sample standard deviation turned out to be 20. At least I'm making that up, but that's what we're playing with here. And that's so far away from 10 that I don't believe this is 10. And how do I know it's far away from 10? Because this chi-square value is so large, it's above 71, right? Once it's above 71, that's when it's too far away. That's when this is too big. And so if this is too big, then I don't believe this is 10, because remember, this was an assumption. And looking back at it, I think my assumption is wrong, so I'm going to reject it. Okay? And if I reject the null hypothesis, I'm rejecting the claim because they're the same thing. So I'm saying, hey, you claimed it was 10. I have some pretty strong evidence that it's not 10 because the sample standard deviation is 20, and that's nowhere close to 10. Okay, so I'm outright saying there's enough evidence to warrant a rejection of your claim. I think your claim is wrong, in essence. Okay, now the other possibility is S could be really small, and it could be something like 5. Okay, so if this was 5, let's see what would happen. So 49 times 5 squared divided by 10 squared, chi-square value would be 12.25. And notice that 12.25 would land in the critical region on the left-hand side. And I would still reject the null hypothesis, right? Because if you land in the critical region, you're rejecting it. The reason I'm rejecting it now is because 5 is much smaller than 10. When it was 20, I was rejecting it because 20 was much bigger than 10. So if it lands over here, it means it's much bigger than 10. If it lands over here, it means it's much smaller than 10. And so 5 is a lot smaller than 10. That's what this is telling me, because 12.25 is landing past below 32. Okay. So you would end up with the same conclusion. You reject the null, which is a rejection of the claim. And so there's enough evidence to warrant a rejection of the claim. But this time you're rejecting it because you believe, again, you don't believe sigma is 10, but have an indication here that it's smaller than 10, a lot smaller than 10. Okay, so anyway, that's kind of how it works. I want to kind of show you that. Now let's do the p-value method. Okay. Again, one thing I want you to notice is no matter what happens here, if the claim is attached to the null hypothesis, there's no way to support the claim. If you look at the different cases that I went through, none of them were none of them had a conclusion where we ended up saying there's evidence to support the claim. And that's because the claim is attached to the null hypothesis. Now, if the claim is attached to the alternative hypothesis and you reject null, then that's when you would support the alternative, which would be supporting the claim. It's the only way to support the claim. If the claim is attached to the null, you'll never be able to support the claim. The best result that you'll have is a failure to reject the null, which would be a failure to reject the claim. And that is, there's not enough evidence to warrant a rejection of the claim, which is what happened in the original problem, right? So going back to the original problem, that's the best scenario that you could a researcher could hope for. We'll never be able to support their claim if the claim is attached to the null hypothesis. Okay, so let's do the p-value method. Okay, so remember with the p-value method, you don't find the critical values, so you don't need to find these. And so you really don't even need to worry about this. Like first step when you do the traditional method is you find the critical values. You start with alpha. And what we did in this case is we said alpha was 0.05. We had a two-tailed test. And so we divided it by 2 and found the area to be 0.025 and then found the critical values where those occurred. You don't have to do any of that at all. Okay. All you do is run the test. Okay. So if you just run through everything we just did again, you run the test and then assume the null hypothesis is true. So you're saying sigma is 10, you're assuming it's 10. And then find the test statistic. Nothing there changes. We end up with 55.056. And now what's different with the p-value method is once you find the test statistic, then you're going to find the area from the test statistic either to the right of it or to the left of it. Now, how do you know whether to go left or right? Look at the alternative hypothesis. So let's say the alternative was sigma was greater than 10, and you would find the area to the right of this statistic from here on up. If it were less than 10, if that was your alternative hypothesis, you'd find the area from here on down towards the left. We have a case where it's not equal to 10, and that's a two-tailed test. And this gets a little confusing, I must admit. Which side do you do if it's not equal to 10? And the answer is depends on which side of this bell you're landing on. The chi-square distribution you're landing on. Are you landing on it closer to the right or closer to the left? It's test statistic, right? Where is it landing? Is it landing closer to the right or to the left? If it's to the right, you'll go to the right. If it's to the left, you'll go to the left. So you just got to figure out which side it's closer to. And the easy way to tell is compare this to this. The sample standard deviation was 10.6. Our assumption is that the population standard deviation was 10. 10.6 is to the right of 10. It's bigger, right? So when you calculate chi-squared, you're going to get 55. Remember, I told you if this was 10, S was 10, and this should have been 49. So 49 is what I would say is in the middle. This happens when S is 10. S equal to 10 corresponds to 49, right? If you plug 10 in here, 10 squared over 10 squared will cancel, and you'll be left with 49. That's kind of the middle. Now we're at 10.6. So when you put 10.6 in for S, it's going to push it up a little bit above 49, and it's going to go to 55 something. And that's what I'm saying. It's pushing it a little more towards the right edge, right tail. And so we're going to find the area from here on up. Okay. Look, if this had been 9.6, and when you plug 9.6 into here, you're going to get a number a little bit below 49. And then you would find the area on the left side, on this left side. I'll go through that scenario just in case you see it in the homework, but let's do this one first. So what we're going to do is we're going to find the area from 55.0564 on up. And that's going to be our p-value. And the way you can do this is on the calculator. You go to what we're trying to find is the area under this chi-square distribution from 55 on up to infinity. And there's a chi-squared CDF function that will do that for us. You'll just have to say chi-squared CDF of the left chi-square value, comma, the right chi-square value, which is infinity. So I'm just going to put in a bunch of nines. And then you do have to put in the degree of freedom because the shape of the distribution changes depending on the degree of freedom. So in this case, it would be 49. So let's see what we get. So go to distribution, scroll down to chi-squared CDF. Then the left chi-square value, 55.0564. Comma the right or the upper chi-square value, which is infinity. So just put in a bunch of nines. And then the degree of freedom, which is 49. Okay, so the area trapped between those two chi-square values is about 0.256. But this is not the p-value in this case. Because when you have a two-tailed test, this is the probability of being 55 or above with your chi-square value. But remember that could also be too low. So there's a probability of being too low. And so you would have to double it. This is the high end. There's also a low end because you have a two-tailed test. So anytime you have a two-tailed test, you have to double the area in tail you find the area of. So we found the area in the right tail. If you double this, That'll be the p-value. I'm just going to multiply this by 2. And so our p-value is about 0.512 to round it off. Okay, so let's finish the p-value method. Once you find the p-value, you compare that to alpha directly. You compare the area here to the area here. And in this case, the p-value is greater than alpha. So if the p-value is greater than alpha, fail to reject null. Greater than or equal to alpha. And that's the same answer we got using the traditional method, right? So the p-value is greater than alpha. We fail to reject null, which is a failure to reject the claim. And again, there's not enough evidence to warrant a rejection of the claim. So that's our conclusion. We get the same answer. Just remember that if it's a two-tailed test, after you find the area in one of the tails, in this case, the right tail, you still have to double it because there's two tails, right? All right, so let me just go back and look and see. So the chi-square value is, or the test statistic is 55.056, and then the p-value is 0.512, and the conclusion is we fail to reject null, and so there's not enough evidence to warrant a rejection of the claim. Okay, so that's what we got. Okay, one other thing, and then I guess we can call it a day. If you happen to make a mistake here, this is a pretty common, like I said, it's kind of tricky when you have a two-tailed test. You have to know which side find the area. And so here's your test statistic, right? If you mistakenly find the area to the left of here, then what's going to happen is when you put this into the chi-squared function in the calculator, you would start at 0, right? Because that's the left chi-square value. It starts off at 0. So you'd find the area between 0 and 55.0564, right? If you mistakenly did it that way, which is wrong, then the amount of area that you're going to get in here is going to be much larger. So let's just see what it is real quick. So, again, this is wrong, but I want to show you just in case you mistakenly do this. You would say chi-squared CDF from 0 to 55.0564 at 49 degrees of freedom. Area trapped in there is 0.744 if you round it off. Then you have to double this. And when you double it, you're going to get something larger than 1, right? When you go to double this to find the p-value, because remember, you have to double it because it's a two-tailed test. When you double 0.744, you're going to get something larger than 1. And that should indicate to you immediately that something's wrong because probabilities can't be above 1. P-value represents a probability, by the way, right? The area represents a probability. So if someone tells you the probability is 1.48 or 1.49 or something like that, it's not possible. Probabilities can't be above 1. So that should be immediately an indication that something's wrong. And what's wrong is you need to find the area to the other side. Find the area on this side. Okay. Then one other thing, and then we'll call it a day. if this had been, let's say S had been 9, okay, and your chi-square value here would have been less than 49, but let's see what it would have been. So it's 49 times 9 squared divided by 10 squared. 39.69. That would have been your test statistic. If S was 9, right? I'm just making this up. But if S was 9, then this would be about 49 something. Or no, 49 something. 39.69. Okay. So then your test statistic is over here. And it's below the middle point, which is 49. Remember, S equals 10 is the middle point, and the chi-square value for S equals 10 was at 49. That's the middle. This makes sense because now you're below 10. This is 9. And that puts you with a chi-square value below 49 at 39. So if this happened, you would find the area to the left over here, right? And so you do chi-squared CDF from 0 to 39.69 at 49 degrees of freedom. And then whatever you get, that'll be the area in here. And then you would double that to get the p-value, okay? So it's a little tricky finding the p-value for the chi-squared case, especially when you have two tails. But that's how you do it, okay? What the easiest way to figure this out, again, is you look at S and you compare it to the null hypothesis, your assumption about the null hypothesis. So here, the null hypothesis is that sigma is 10. If S is below that, then it's going to be a left tail where I find area. I'll find the area in the left tail. And if this is above 10, then I'll be finding the area above 10 in the right tail. Okay, so that's the easiest way to tell. Okay, and one other thing I can think of, and then real quickly, because we're almost out of time. The only other thing I can think of in the homework that you might run into that might be a problem is sometimes they give you the raw data and they don't give you the standard deviation from the sample. Let me just check and see if that's the case. This one's close to doing that. I don't think, let's see, let me read through this one. So number 3, okay, it says the data show that men between the ages of 20 and 29 in general population have a mean height of 69.3 with a standard deviation of 3.1. A baseball analyst wonders whether the standard deviation of heights of Major League Baseball players is less than 3.1. So what they did is they randomly picked 20 players and found their heights. And this is the data, the heights of the 20 players that they picked at random in inches. So then the issue that you're going to run into here is they didn't give you the standard deviation from the sample. All they gave you was the sample raw data. So let me just quickly show you. I'm not going to go through the whole problem. We don't have time, but I'll show you how to approach this. Okay, so if you look at this problem, claim that they're making is that claiming that an analyst wonders whether the standard deviation of heights of Major League Baseball players is less than 3.1, which is what it is for the general population for men between 20 and 29. Okay, so the claim is that the sigma is less than 3.1. This is the population of all heights of all baseball players. Okay, and so let's start with the claim. They're claiming that if you look at the standard deviation from this population, sigma, they're claiming that's less than 3.1. So there's our claim. All right, and that is the alternative hypothesis because it doesn't have an equal sign in it. And h sub 0 would then be that it's equal to 3.1. Well, less than or equal to, but we think of that as just being equal to. Remember, the null hypothesis has the equal sign in it. Okay, so to test the claim, they sample, I believe it was 20 baseball players. Yes, so they randomly picked 20 baseball players and they gave us the raw data. So these are the heights of the 20 baseball players. So the problem is, we know we sampled 20, but we don't know what the sample standard deviation is because they didn't give it to us. So what you would do is go to stat and then edit and just enter all 20 of the heights, your raw data, into L1. And then remember, you can go to stat. After you enter it in, you go back to stat, and this time you go to calculate, then go to one variable statistics, and scroll down to S sub x. That's how you're going to get the S. So you go to stat, calc, and one variable statistics. And if you scroll down to S sub x, that will give you the standard deviation that you need here, your sample standard deviation. And of course, you're going to have to put the 20 numbers into L1. Then once you know what this is, then you can go through and calculate the statistic, plugging it into here and whatever. Okay. That's what you have to do in that case. Okay. If they give you the raw data, you're just going to have to calculate the standard deviation on your own, sample standard deviation on your own. Okay. And you can do that on the calculator. You just have to, put the data in first. Okay. So that's it. That's 8.4. Remember, the next test is over chapter 7 and 8. We're done with both chapter 7 and 8. So, try to get the homework done as soon as you can, and then you can look at the practice test, and then take the test next week over chapter 3, or over test 3 over chapter 7 and 8. Okay. All right. So, does anybody have any questions about anything before we end it? Okay. I guess we'll end it there. And then tomorrow, I guess we'll start chapter 9, and that'll be the last right, chapter 9, 10, and one section 11. That'll be the last test. Okay. So we'll start that new material tomorrow. Okay. I guess we'll end it there. Have a good day, and I'll see you tomorrow. And if you have any problems, just email me. Okay. Okay. Bye bye. Have a good day.